it's important to make sure that you can connect the definition of the integral in its limit form with the actual integral. Now, this isn't like a huge emphasis in an AP calculus course. However, you do need to remember that the integral symbol we're using really just represent a limit. So, if we're told that for instance, the interval 2 to 7 is partitioned into n subintervals of equal length, and your change in x is 5 over n, and c sub k denotes any point in the kth subinterval, then the question is what integral would we represent this as? Well, we know that the limit of the sum turns into the integral symbol, and what happens is that a lot of these subscripts, like the k and the n, they're not really used in our integral notation. What is used are the beginning and ending values on our interval. So that we're finding the sum on the interval 2 to 7. The delta x turns into a dx. And then the question is, what function are we actually evaluating these x values with? And you can see that the c sub k's are being plugged into what looks like 6x cubed plus 5x. So as crazy as that problem looked, it's actually pretty easy. It's more just recognizing notation, or being able to convert between this awkward limit notation and writing it in summation, into integral notation. Now let's actually evaluate some definite integrals. Now the only real tool we have on our tool belt is using geometry, right? We know areas of rectangles, triangles, circles, if those show up. So that's all we have. So in order to evaluate this integral, 2x plus 1, I'm going to have to sketch a picture. So you're going to have to know how to sketch 2x plus 1. And I'm only sketching it on the interval 0 to 3. So at 0, when I plug 0 into 2x plus 1, I get 1. And when I plug in 3 into 2x plus 1, I get 7. And I know that's a linear graph, a linear function. Okay, and so the integral is asking me to compute this area. So we have a couple options. I think I might just break it up into a rectangle and a triangle. So I might view it separately as this blue rectangle. Now the blue rectangle has area 3. And this triangle here, the base is 3, and the height, this is certainly not drawn to scale, but the height would be 6 here. So the area of this triangle here would be 1/2, 3 times 6 would be 9. So the definite integral would have a total area, or a final value, I should say, of 12. Alright, so notice our reliance on geometry there. And I mean, really the exercise at this point is just to be able to understand what integral notation is requiring you to do in terms of what the lower and upper limits of integration are, etc. Let's try another one. Negative 2x plus 2 on the interval 0 to 4. So we're going from 0 to 4, and at 0 I've got a y value of 2. At 4 I've got a y value of negative 6. This is again not to scale. And that is also a line, so we're looking at this. So with the definite integral, according to the definition of the definite integral and some of its properties, we're going to want this area and this area, remembering that the area below the x-axis needs to be counted as negative. So that suggests we probably need to know this point here, that changeover point where the function goes from positive to negative. So let's set the function equal to 0. We could probably do this in our head, but negative 2x plus 2 is 0 precisely when x is 1. So this must be a 1. And now I can find the area of this left triangle here. So that has a base of 1 and a height of 2. So 2 times 1 divided by 2 is 1. And over here, this has a length of 3 and a height of 6, or we could say negative 6. The area that would be 6 times 3 divided by 2, and 6 times 3 divided by 2 is 9, but I'm going to count that as negative 9. So the total area would be 1 plus a negative 9, or 1 minus 9 if you view it that way, but in the end it's negative 8.